time to do an example in spherical coordinates. But first, let's talk about coordinate systems in general. If you have a nice standard x, y, z three-dimensional coordinate system, and you go over x, and you go over y, and you go up z, you get to the point x, y, z. You already know that if you go an angle theta in the xy plane, and you go out a distance r, according to polar coordinates, and then you go up a distance z, you get to r theta z, which is exactly the same point in what we call cylindrical coordinates. Here is how spherical works. Instead of having linear dimensions, it has mostly angular dimensions and only one that's linear. Here's rho. Rho is quite simply the distance to the pole, to the origin. The other thing is that theta is theta. Theta is the same as in cylindrical. So if you come over an angle theta, and if you come down an angle phi, or phi, depending on how you want to say that, this is the angle from the zenith. It's the declination here. You go down, and then you go out a distance rho. So if you know angle, distance, you have rho, theta, phi. And that's spherical coordinates. Now, some things are pretty obvious right away. For one thing, rho has to be this: the square root of x squared plus y squared plus z squared, because that's the distance from x, y, z to 0, 0, 0. So that's pretty easy. Remember, r itself is x squared plus y squared because z is not involved. R is just the distance in the xy plane. A few other fun facts. I've picked out this triangle. Notice this is in the plane and this is vertical. So this is a right angle. It's that guy. Here's r, here's z, and this is phi because of opposite interior angles. These are parallel lines. This is a transversal, so your angle phi is equal to this opposite interior angle, also phi. Here's rho, here's z, here's r. So that tells us a few things right away. For example, we know that the tangent of phi is going to be r over z. Okay? We also know that if you take z and divide by rho, that's adjacent over hypotenuse, you're going to get cosine. So z is rho cosine phi. And we also know this: r is equal to rho sine phi, because r, the opposite side over the hypotenuse, gives us the sine of phi. What does this tell us? Well, it tells us quite a few things. For example, we know that x equals r cosine theta. And we just found out that r is rho sine phi. So that's how you write x in spherical. Y, by the same token, is r sine theta. So it can be rewritten as rho sine phi sine theta. And we finish off the set with the one we just did over here, rho cosine phi. Here is a conversion of x, y, and z into spherical coordinates. And here are conversions for r into spherical. And, of course, we know that theta is theta, so there's no conversion between cylindrical and spherical for that. Okay? Now let's talk a little bit more about what happens. I'm not going to prove this next part. I'm simply going to cite it. You can read more about it from other sources. Remember that dv, dx, dy, dz, in some order or another if you're using rectangular, or r, dr, d theta, dz, in some order or another if you're using cylindrical. And here's the one that is not very intuitive. Rho squared, sine phi, d rho, d phi, d theta, or some order. The rho squared is performing the same surface that r performs up here. Because remember, the theta in radians is dimensionless. So if you're in rectangular, linear units, linear units, linear units, that's linear cubed or length cubed, cubical units for volume. Makes sense. But if you look at this one, linear units, no units, linear units, that would just be length units squared, except that we have the r providing the missing dimension. Similarly, this is the only one rho that has units of length. This is in radian measure. This is in radian measure. These two are dimensionless. We actually need two factors of rho to make up the difference. And the way this works, there are various illustrations that show you that, but like I said, I'm not going to do that right now. Instead, I'm going to look at a particular problem with one of our old friends, the cone. And let's suppose that the cone is of height 2, and the half angle right here is pi over 6, or basically 30 degrees. Okay? Now here's something that you have to watch out for. If you were going to compute in spherical coordinates over this region, theta is going to go all the way around, because this is a solid of revolution. Phi, now remember, we measure phi from the vertical, from the zenith, and so we would go down to pi over 6. Okay? And rho would give us a little bit of a problem, because rho goes from the pole, the origin, until it hits the upper surface. And the upper surface is z equals 2. Now remember, z equals 2, z equals rho cosine phi. Put the 2 in here. Solve for rho. 2 over cosine, or 2 secant phi. 2 secant phi is our upper limit of integration for our region. Okay? And in general, if you have a cone with a half angle of alpha and a height of h, you can use this information to describe the region in spherical. Let's talk about a particular problem. Let's suppose we want to find mxy for the cone. You know what mxy is. It's the triple integral of z times density dv over our solid region E. Okay? Now, let's say, in this case, to keep things simple, that the density is a constant 1. All right? Let's set up the integral. Using the limits of integration that we came up with, we can say that mxy is going to be the integral from 0 to 2 pi, that's for theta, 0 to pi over 6, that's for phi, and 0 to secant phi. Then we have z, which we're integrating. Our density is 1, and then dv. Remember dv? dv is a real treat. Rho squared, sine phi, d rho, d phi, d theta. We have a problem. The integrand isn't quite right. By which I mean, we have a z in there. That's not spherical. But we do know what z is. Z happens to be rho cosine theta. So put in rho cosine. Did I say theta? I should say phi. Okay, so that takes care of him. And we have rho squared sine phi d rho d phi d theta. Okay, I'm going to do something which is kind of bad form, but is going to save us a bit of trouble. Do you see any thetas in here? None of this is in terms of theta. So this outer integration from 0 to 2 pi with respect to theta is just going to give us a 2 pi. So here's a mischievous shortcut that I like to use occasionally. Ordinarily, you're not supposed to integrate from the outside in. It's supposed to be from the inside out. Let's see, this is rho cubed. We have cosine. We have sine. And we haven't done the integration with respect to rho or with respect to phi. So let's take care of that. The first integration is pretty straightforward. Rho cubed becomes rho to the 4th over 4 from 0 to 2 secant phi. And we still have the cosine, we still have the sine, and we have d phi waiting its turn. So here's 2 pi. Here's the 4. Okay. 4th power of 2 secant phi. Well, 2 to the 4th is simply 16. Secant to the 4th power, cosine, sine, and the differential. Okay. Well, 2 pi over 4. 4 cancels with the 16. We have a 4. We have 8 pi out front. And we know what secant is. Secant is the reciprocal of the cosine function. So cosine cancels one of the secants, and we end up with cosine to the minus 3 sine phi d phi. And here's something useful. The derivative of cosine is minus sine. So we're missing a minus 1. We get cosine phi to the minus 2 over minus 2 from 0 to pi over 6. The minuses cancel. 2 is in the bottom, so we have 4 pi. And we're going to get cosine pi over 6 to the negative 2 minus cosine 0 minus 2. Let's see, what's the cosine of pi over 6? That's root 3 over 2, isn't it? So if you square it, you're going to get 3/4. And if you're taking the reciprocal of it, you're going to have 4/3. So there's going to be 4/3 right here. And this is going to be minus 1. So when we finish computing this, we get 4 pi times 1/3. We get 4 pi over 3. We just computed the moment with respect to the xy plane for the cone.